You've definitely seen these things around, those little boxes with the super crisp digital displays, the digital voltmeter. But have you ever stopped to wonder how it actually works? I mean, how does it take something as invisible as electricity and just pin a number on it? Well, we're going to peel back the cover and look at the incredibly elegant trick that makes it all happen. I mean, that's really the fundamental question, isn't it? Voltage is this invisible force, this potential. You can't see it, you can't hold it in your hand. So how in the world do you measure it so precisely? It's not like you can just look at it. You need a really clever workaround. And that workaround is performed by the hero of our story, the digital voltmeter, or DVM. Its entire job, its whole reason for being, is to take that invisible, kind of fuzzy analog voltage and translate it into a sharp, clear digital number that we can actually use. And don't let the name fool you. Yeah, it's a voltmeter, but it's really a Swiss Army knife, with some pretty simple add-ons that can turn things like resistance, or temperature, or even pressure into a voltage. The very same device can measure almost anything. It's just unbelievably versatile. Okay, so what is this brilliant trick I've been talking about? It all comes down to one simple, powerful idea: voltage to time conversion. See, instead of trying to measure voltage directly, which is hard, the DVN changes the problem into something way, way easier to solve. Just think about it for a second. Measuring an abstract, invisible potential, that's tricky. But measuring time? That's easy. We've got clocks, we've got stopwatches, we know exactly how to count seconds. The pure genius of the DVM is that it turns the hard problem into the easy one. It turns a voltage measurement into a time measurement. All right, so here it is. This is the secret sauce. The DVM's entire operation is built on this one idea. It precisely measures the amount of time it takes for a voltage to drop from whatever level you're testing all the way down to absolute zero. Now, to make this super easy to picture, let's think of it as a race. The voltage you're trying to measure, that's the starting line. 0 volts, that's the finish line. And the logic is just dead simple. A higher starting voltage means it's going to take longer to get to the finish line. It's that direct. A higher voltage means a longer race. So how does this race actually happen inside that little plastic box? Let's meet the key players, the components that are going to run this race, time it, and give us our final number. First up, every race needs a runner. In our DVM, that's the ramp generator. Its whole job is to create a voltage that falls at a perfectly steady, perfectly predictable rate. Think of a runner who just never gets tired and never changes speed. That constant linear drop is the key to everything. Of course, you can't have a race without officials. For us, those are the comparators. We've got 2 of them. The first official is watching the starting line. The second our runner's voltage matches the one we're trying to measure, it yells, "Go!" The second official is waiting patiently at the finish line, at 0 volts. And the instant our runner gets there, it yells, "Stop!" So what do those go and stop signals from our officials actually do? They control the gate. And you can think of the gate as literally the start/stop button on a digital stopwatch. The first comparator's signal pushes start, opening the gate. The second one pushes stop, closing it. Simple as that. And what is that stopwatch actually counting? Well, it's counting pulses from our timekeeper, the oscillator. This little guy generates a stream of incredibly precise, evenly spaced electrical pulses. It's like someone clapping at a perfect, constant rhythm. These are the ticks of our internal clock. Okay, let's put it all together and watch the race. The ramp generator starts its steady drop. The instant it matches our input voltage, the first official yells "Go!" and that gate flies open. Our clock pulses start pouring through. The ramp keeps dropping, 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 until it hits 0 volts. Bam! The second official yells "Stop!" The gate slams shut, and the flow of pulses is instantly cut off. So, the race is over. The stopwatch has been stopped. The DVM has perfectly captured a specific duration of time. But how do we turn that little collection of clock ticks into the number we actually see on the screen? Well, all those little pulses that squeeze through the open gate had to go somewhere. They flow directly into a set of circuits called decade counting units, or DCUs. You can think of these as the official scorekeepers. They sit right behind the gate, and their only job is to count every single pulse that gets through. So the race finishes, the gate is closed, and our scorekeepers, the DCUs, tally up the final count. Let's say, for this race, they counted exactly 1,735 pulses. That number, 1,735, is our raw data. It's the direct measurement of how long that race took. And here is the most beautiful, elegant part of the whole system. The circuitry is designed and calibrated so that the raw count of pulses is the voltage reading just with a decimal point. So 1,735 pulses becomes 1.735 volts on the display. The problem is solved. The time we measured literally is the voltage. But of course, voltage isn't always stable. A single measurement isn't good enough. So there's a tiny internal timer, basically a reset circuit, that immediately clears that count back to 0 and tells the ramp generator, okay, new race, let's go. This whole thing happens over and over, many times a second, which is why we get that constantly updated reading. So you might be thinking, wow, okay, that's a lot of steps with ramps and gates and clocks. Why go through all that trouble? Why does this clever little trick matter so much? Well, here's the bottom line. This method is brilliant because it turns a really abstract, difficult problem, measuring an invisible potential, into one of the simplest tasks for a digital circuit, counting. It forges this perfect linear link between voltage and time. And you should know, this isn't just for voltmeters. This foundational idea is the beating heart inside countless digital tools we rely on every single day. And that kind of leaves us with a final thought, doesn't it? We just saw how this invisible force, voltage, can be measured just by turning it into time. It really makes you wonder, what other invisible forces, what other abstract ideas out there, from magnetism to maybe the concentration of a chemical, could we measure if we could just find a clever way to turn them into a race against a clock?